This lesson is going to walk you through the different types of intermolecular forces. So the goal of this lesson is we want to be able to identify the different types of intermolecular forces. And specifically, we have two kind of essential questions that we're going to answer throughout this lesson. So they're right here. We want to make sure we can discuss how we measure intermolecular forces. And we also want to talk about the factors that contribute to how strong these forces are. Okay. So to get started, first we're going to just kind of jump back to the very beginning of these notes when we started talking about bonding. Remember, we talked about the different types of these three different substances all melted at different temperatures, essentially. So our wax melted first, then the sugar, and then the salt. So if we think about what type of bonds these are, right? I know we discussed ionic bonds. Ionics have a metal, which is sodium right here. So this is an ionic bond. And then these are covalent bonds because they have all nonmetals. So if we kind of think back to some of the things we've learned about different types of bonds, we know that covalents have lower melting point, so that's why these were able to melt, and ionics have higher melting point. So what we want to do today is really focus on explaining why these, well, that's not what I meant to do. Why these two substances, let me just change the color here. Why these two substances here, okay, my two covalent substances, why did it take longer for my sucrose to melt? And remember, one of the theories that we said in class was maybe it has something to do with what makes up the formula. Like sucrose, the formula is different. It has an oxygen in there. So maybe something with that oxygen affects how fast something is melting. So we're going to kind of switch over. We're going to look at a few kind of tables and charts and see if we can start looking for some patterns that could help us figure out how we can measure our forces of attraction. Okay, so just to kind of get started, just a review. We know this is a solid, this is a liquid, and last one is a gas, right? Because we discussed how gases are really spread out and solids are tight, uniform arrangement together. And we also talked about how our gases have weak forces of attraction and our solids have our strong forces of attraction. It's these forces of attraction that we're going to talk about today. So we're actually going to name these forces of attraction. Remember, we've mentioned before how we have intramolecular forces. Those are like the actual bond. So we are not talking about types of bonds today. We are talking about intermolecular forces. These are the forces that exist between molecules, okay? So we'll go through all these different types today. So the first question we kind of want to answer is we want to talk about what's stronger. So again, these up here, these are my intramolecular forces. We're not really going to talk about those today. These are my types of bonds. And I know these are very strong because they are a bond, right? In order to break the bonds, we have to do something like cause a chemical reaction in order to break those bonds. So I know those take a lot of energy to break, like something like fire, right? Lighting something on fire, an explosion. Usually you're heating something up, or you have to have this right environment to cause those bonds to break. We're going to focus out here. So if I was to think about which is stronger, right, that usually means something strong. That means it needs a lot of energy to break, right? It's going to take a lot of energy to break that. So here, hydrogen bonds, right, these have the most energy. And then my London dispersion, that has the weakest energy. So I can kind of put these in order just as I'm thinking. Hydrogen bond is probably the strongest. Then we have something called dipole-dipole. And then we have our London dispersion forces. This is our weakest. Okay, so we're going to kind of start talking about how can we start measuring the strength of these forces. Okay. So let's go over here. We're going to look at tables 2 and 3. So I'm going to kind of scroll right here. All right, so I want to give you a minute to kind of go through these two tables 2 and 3, and answer the questions. So you're going to stop right here. Oopsie. You're going to stop right here. Okay, and I'll kind of show you what you're doing. So essentially all we're doing here is kind of like what we did in class, where we're just going to look at the electronegativity difference between our molecules, and we're going to kind of think about, okay, is this a polar or a non-polar substance? So like for example, carbon and hydrogen, right? I get a 0.4 is the difference if I subtract their electronegativities, and we know that that is a polar bond. Okay, and then you're just going to kind of do the same thing with all of these. Just subtract and then compare to your chart and call it polar or non-polar. Okay, and then try to answer the questions. Down here, I'll go ahead and fill in the state of matter. Fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a gas. Okay, so go through, read those, and then answer these questions. And just pause the video while you do that, and then just start it back up when you're done. All right, I filled in the chart. These I'm going to put a little question mark by. I don't have my electronegativity chart with me. I think those might be close. Essentially, what we're seeing is they're all polar, okay? So if I complete the statement, I can kind of see that as I started lower here and as I kind of get higher up, we're starting to see that the electronegativity, I think this might actually be 0.9 now that I think about it. The more polar the molecule, the higher the boiling point. So I'm starting with a negative temperature and I'm getting higher the more polar I have. So if we're thinking about the forces needed to boil something, right? That means we're changing from a liquid to a gas when we boil. That means that if I have a liquid, right, and it has these attractions between these molecules, I'm breaking those attractions. if I need a lot of energy, a lot of heat in order to break those attractions, that must mean that they're very strong. So the more polar, the higher the boiling point, the stronger the intermolecular forces. Okay, so we can use boiling point to measure how strong our forces are. For these, all of these are non-polar. Okay, and essentially my molar mass, that just means like you're adding up the mass number for each one. So if this is fluorine, there's 2 fluorines. I would look at fluorine's mass number on the periodic table, and I would add that up. Trying to remember fluorines off the top of my head. I want to say it's like 19 or something. I know chlorine is 35, and there's 2 of them, so we'll say 70. I know bromine is about 80, so for 2 of them would be 160. And I know that iodine is greater than 160. Essentially, we're increasing, right, as we're moving down the chart. So if I wanted to fill in my chart here, okay, I could say that as my mass increases, right, so does my boiling point. So that must mean that the molar mass, as the molar mass increases, the IMFs are getting stronger as well, right? Because, how did I know that? Because higher the boiling point, the stronger the IMFs, okay? All right, let's take a look at some of these graphs over here. We'll kind of do this part together. Essentially, this table here, this question is just asking if this chart matches up with what we saw on the other charts. It's just talking about essentially how as my mass of my substance, as my substance gets bigger, the size is bigger, it has more mass, the boiling point is going to increase. So that matches pretty much with what we've already seen. For question 18 and 19, we're looking at this graph 1, right? So take a minute, pause the video, and just go through and see if you can answer these questions. All right, so for question 18, we're just comparing these 2 substances, and I'll kind of circle them right here. And it's asking which one has a stronger IMF. So remember, we just said we can use boiling point to help us measure the strength of IMF. So the higher the boiling point, right, the stronger the intermolecular forces. So I know that 10 tetrahydride has the smallest, or the largest, strongest intermolecular forces. Okay, and I can tell because the boiling point is highest. Okay. C is essentially just restating what I said. Higher the boiling point, the stronger the IMF. Okay. For question 19, we're looking at, erase those circles. We are looking at how in my top line, this red line here, the trend doesn't look the same as it does for the bottom line. This line, the trend is going up this way. In the red line, I go down before I start to go up. So what it's really asking us is which has stronger forces, H2O or H2S? And again, we're just looking at our boiling point. Which one has the highest boiling point? H2O. So higher boiling point equals stronger IMFs. Okay. This last one, we're answering these couple of questions based on this graph. We're looking again at these outliers of our trend. So instead of going up straight on our graph, which is essentially kind of showing like the size. So as the size is getting bigger, we're seeing our intermolecular forces getting stronger, but we have some of these exceptions. Okay, so the three compounds that deviate are H2O, HF, and NH3. Okay, and so what it's saying is they have stronger forces than everything else in their other line, because the higher the boiling point, the stronger the IMFs, right? And then what this is really doing is it's starting to bring up the topic of hydrogen bonds. Okay, a hydrogen bond is when hydrogen is bonded to either oxygen, like water, fluorine, like in HF, or nitrogen, like in NH3. Okay, so anytime I have hydrogen bonded to these three atoms, we have something called a hydrogen bond. And essentially that means that it's going to have a higher boiling point because it has a stronger force. Okay, so let's kind of take it back to this here. I'm going to kind of scroll because we've just gone over all of this together. So here are your definitions that you can use to write in your notes. So if you kind of look on your notes page, or if you just want to make a chart, on notebook paper, that's fine. We just want to list the different types of forces based on their relative strength. Okay, so we've already said how a hydrogen bond is the strongest. Then we have dipole-dipole. And then we have London dispersion forces. Okay, and then we're just going to write a little description in there. So here's your description. So again, we said a hydrogen bond is just hydrogen bonded to F over N. Essentially, it's creating a very strong, partial charge, opposite partial charges. So this is a very strong attraction between these two atoms. And so they call it a hydrogen bond. Don't let the word bond confuse you. It is not an actual bond. When this was first discovered, they thought it could be because it was very strong, but then it was discovered that it wasn't. So, but the name just kind of stuck. So just make sure it is not a bond. Okay. The second one is dipole-dipole. This is essentially just an attraction between polar molecules. So we talked about how opposites attract. So when I have a polar molecule and I have these partial charges are going to attract each other. It's not going to be as strong as a true ion, like an ionic bond, but there is some attraction there that can help hold those molecules together. Okay. Essentially, a hydrogen bond, right? Since we have partial charges here, hydrogen bonds, if you have a substance that has a hydrogen bond, it will also have dipole-dipole because it has those partial charges as well. Okay. All right, lastly is London dispersion forces. This one's a kind of confusing to think about. You kind of have to think about, remember that electrons are always moving inside an atom. They're not, remember, just sitting pretty in those beautiful rings like we like to think they are. They're always moving around. So when that happens, sometimes on accident, you kind of think of them like marbles, they all end up on one side of the atom. When they do that, we end up with this partial negative charge on that side of the atom. Okay, so it's not a polar molecule. I'm not saying that they're always on that side of the atom or the molecule, but because they're sharing and the electrons just move, right? There's no one controlling where they're moving to or making sure they're staying even. They're just moving. And so every now and then you end up with this unbalanced kind of unbalanced marbles is the way to think of it. And so you have this little partial negative charge where your electrons end, and then over here where there are no electrons, you have a little partial positive charge. Okay, and then, so like if I have two of those atoms, right, where I have this partial negative charge here, and then this one also has a partial negative charge, it's going to be attracted to this positively charged area of this atom. Okay, so what this is saying is like these little electrons are going to be very attracted to this positive nucleus because the other electrons are all away from on the other side of the atom. So they're out of the way of this attraction. These are considered a temporary dipole. Okay, so this is a very short-lived attraction, and just as fast as you have these particles here on this side, they could just as easily move over here to this side and create the opposite effect. Okay, so these are always essentially moving, creating these temporary dipoles. I can have temporary dipoles or London dispersion forces, temporary dipoles in a polar molecule as well. So, and an atom that has a hydrogen bond, because I could always be, again, these electrons are still moving through here, sharing in this space. I could have a moment where maybe, all the electrons are over here in oxygen, so it creates a much kind of stronger negative attraction, and it could attract another, partially positive atom like this right here. Okay, so just know that if I have an element with a hydrogen bond, it has dipole-dipole and LDF also. If you have something with dipole-dipole, it also has London dispersion forces. London dispersion forces only occur in non-polar molecules. So that means that you cannot have hydrogen bonding or dipole-dipole if you have non-polar. If you have a non-polar molecule, you will only have LDF forces. Okay. Last thing is there's some factors that affect how strong our intermolecular forces are. So just like when we were looking at the data charts, we saw that the larger the molecule, or essentially the size, okay, the molecular weight or the size of the molecule as it gets bigger, okay, your IMFs are also going to get stronger. Okay, same thing with polarity. As it gets more polar, right, then we have stronger IMFs. Okay. Distance between the molecules also plays somewhat of a role, especially for London dispersion forces. If I have this is like a gas or a liquid. Let's compare like a liquid to a solid. Your liquid is spread out a little bit, right? And so these forces are going to be a little bit weaker just because they're further apart than if you had a solid, right? These particles are very close together. They're interacting much more, so they're stronger as compared to a liquid. All right, so just make sure you can kind of go back and answer that essential question. The key takeaways, they should kind of help you answer those two essential questions. So make sure you fill that in on your notes. You can just write it in at the top or on the bottom if you have an older copy of the notes. And then I want you to take a look at the practice problems. So we can do one together really quick. If you feel confident, you can just skip this part. But we can kind of do one together. So let's do HF. So I'm going to just draw my Lewis structure. Okay, I know I'm going to have 8 valence electrons. Okay, I want to do my molecular shape, so that's linear. And then I'm also going to do my molecular polarity. So I want to look at my electronegativity difference. Fluorine is 4.0, hydrogen is 2.1. So the difference is 1.9, so definitely polar. And fluorine is my most electronegative. It's going to get my partial negative charge. Okay, so I have a polar molecule because I have a negative and a positive end. My ends are different. Okay, so because I have a polar molecule, right, I can go ahead and write dipole, dipole. I know that as soon as I have a polar molecule, I know dipole, dipole forces are going to be present. And because I have dipole, dipole, I also have London dispersion forces. Okay, the last thing I need to check is my hydrogen bonding. So remember, hydrogen is bound for hydrogen bonding. Let me just write it over here. I like to think of it as FON, kind of like fun, but FON. So if it's an H bonded with any of these, then you know it's hydrogen bonding. So we have an F over here. So I know that this is an H bond. Okay. Let's look at I believe I don't have a periodic table on me. But I believe this one has 4. And then this is going to be 28, so that's 32. So I'm going to put my fluorines all around the outside. Okay, and I may have to pull up a periodic table really quickly so I can get the, here we go, electronegativity for silicon. That is not it. Maybe this is it. Here we go. All right, silicon is 1.8 and fluorine is 4. Okay, so let's go back over here to the notes. So 1.8 and then 4. So that is definitely a polar, because that's what, 2.2. So fluorine is definitely going to hog those electrons. So it's going to get all those partial negative charges. Okay, and then silicon has the partial positive. So remember, to do my shape, okay, I have 4 things that are bonded, so that would be a tetrahedral. And then to do my polarity, all of my ends are the same. So all of the ends of the molecule are negative. So this would be non-polar. So if I think about my IMFs present, I have to think about which ones are present in non-polar molecules, and that would be London dispersion forces. Okay, so because this is a non-polar molecule, I cannot have any dipole-dipole charges or attractions. Okay, so even though it has a polar bond, the molecule itself is not polar, so it will not have any dipole-dipole interactions. Okay, so it can only have LDF attractive forces. Okay, so try to do these last ones. I will post a key at some point, or there'll be one in class you can kind of check your work with, and just let me know if